this video we're going to look at the first derivative and everything that it can tell us about a function as we now proceed to concern ourselves with sketching functions. So the first derivative determines when the function goes up or down. Of course, you can determine that a variety of ways. By looking at the graph is probably a good option, but we want to learn to get those same ideas and results from looking at our first derivative. So how do we do that? Well, when the first derivative, f prime of x, is positive, the function is increasing. So f of x increases. And that just means the function gets bigger since the tangent slopes are all positive. So you might not have noticed that before, and maybe you have, but if the tangent slopes are positive, your y values are going up, your function is getting bigger. And if that makes sense, you shouldn't be shocked that if the first derivative is negative, and keep in mind that can happen over a whole entire interval of x values, not just a single x value, but an infinite number of x values. If your first derivative is negative, your function is decreasing. Your function is getting smaller since the tangent slopes are negative. So positive tangent slopes, function goes up. Negative tangent slopes, function goes down. And just some definitions and stuff. Now, this is probably going to be a little bit too much all at once, but we'll sort this out in future videos with some examples. And just to make some mental notes or maybe even physical notes here, a function has a stationary point at an x value x equals c if and only if the first derivative is equal to 0 when you input that specific x value. And c is just some concrete x value. And what that means is the function is standing still at x equals c, and hence the name stationary point, and the function is not increasing or it's not decreasing. And you probably can recognize as well that's the location of a horizontal tangent slope. So stationary point simply means you have a horizontal tangent slope. And something we'll be considering all the time now when we're sketching curves is a critical value. So what exactly do we mean in calculus by a critical value? Well, a function has a critical value at x equals c if and only if, not surprisingly, the last thing we saw, if your x value of c makes your first derivative 0 or undefined. And that's a strange one, but just keep in mind, when could your first derivative be equal to 0? Well, of course, that's the location of any horizontal tangent slope. And some of those will be stationary points, and some of those will be something even a little more special than stationary points. And when can your first derivative be undefined? Well, a couple of reasons. You might have a vertical tangent, so you might have an undefined tangent slope because your tangent is actually straight up in the air, a vertical slope. You might have a sharp point or cusp, and you might even have some kind of a discontinuity, a vertical asymptote, oscillating discontinuity, jump discontinuity. That pretty much does them, summarizes them all. So just keep in mind, when I say critical value, you're going to get your first derivative and try to figure out what makes your first derivative 0 or even undefined. And the last new definition, which is really not new, you've heard this term before, a function has a turning point at x equals c if and only if you have a horizontal tangent slope there. So if x equals c, that c value makes your first derivative 0. It means your horizontal, your tangent slope is horizontal, and it means you may have a turning point. And also, confusingly, a turning point can also happen when the first derivative is undefined. And we'll worry about that later, but it's just kind of they small print, I guess, at this point in the legalese of setting up our definition. So, of course, that's a horizontal tangent. So if you have a horizontal tangent, you should suspect a turning point. If your first derivative is undefined, you should also suspect a turning point. And how the heck could that happen? Well, it can't be a vertical tangent. There's no way a turning point can happen at a point of vertical tangency. There's no way a turning point can happen when your function's undefined at a vertical asymptote or such. So it has to be just a sharp point or a cusp, and you're not going to encounter those every single time for sure. So focus on mainly turning points happening at horizontal tangents, and the odd time it could also happen at a sharp point or cusp in some weirder functions. And there's an important and here as well. It's not enough just to assume that you have a turning point when your first derivative is equal to 0. You have to confirm that your function actually turns around, and hence the name turning point, because I'm sure you can think back to your pre-calculus training. sometimes, especially at roots, you can have a root that hesitates and keeps moving forward. So it keeps increasing and doesn't actually turn around with multiplicities of like 3 and 5. And if you've forgotten all that, don't worry, we'll look at that through some examples. So a turning point has to actually turn around. The function has to turn at the turning point, and that should make sense. And we'll confirm that on a few examples as well and show you how you can do that analytically and also by looking at the graph. And there's another note here. Of course, if it changes direction, I mean it's going from increase to decreasing or vice versa. Okay, let's try to put some of those new terms together here. We won't cover everything here in this first example, but this is f of x equals x squared minus 4x, as you can see typed into our Desmos graph here. And I have a tangent line attached to our function. And of course, I guess the point of tangency is an a value of some kind of an a value. Let's make that 0 instead of negative 0.2. And of course, we can see that we have a negative tangent slope there. Okay? And we also know we're pretty much experts in terms of quadratic functions. There's not a lot to see, but I just want to show you that I know this function's decreasing whenever that tangent slope is negative. Right, so all the way off our graphing screen here, all the way down until, of course, we hit a horizontal tangent. So that function's still decreasing. So the y values range, no pun intended, from up towards positive 5 all the way down to that minimum value of negative 4. So here is a kind of a weird notion, but the calculus doesn't lie and our definitions don't lie. Our function is not increasing or decreasing there. So there's a stationary point because we have a horizontal tangent slope. It's also a turning point because I'm sure you know that the function is turning around and now it's getting bigger. And notice it's going up and the y values are increasing. And that is also evidenced by the positive tangent slopes. So just quickly again, when you see negative tangent slopes, functions going down, y values getting smaller. If you see a horizontal tangent, you automatically have a stationary point because your function's not increasing or decreasing there. And if your function actually turns around, changes direction, that stationary point is a turning point. And notice now our tangent slopes are positive and our function is getting bigger and bigger and bigger and goes off the screen. Okay, as we conclude this video, let's find the intervals where this quadratic function, x squared minus 4x, is increasing or decreasing, relying not on Desmos, but of course on pencil and paper. So as soon as you read increasing or decreasing intervals, first thing that should jump in your head is, of course, look at your first derivative. Because it's the sign of your first derivative that's going to determine where a function goes up or where it goes down. And differentiating a quadratic is pretty straightforward. Power rule twice, so the derivative is 2x minus 4. So there's very little mystery surrounding a quadratic. We obviously know what a quadratic looks like. We know what its end behavior is. We can even determine the vertex of this quadratic pretty quickly. So we don't necessarily have to rely on any advanced methods to determine where the quadratic is going up or going down. But to get us ready for more difficult functions, instead of just relying on an inequality here, which of course it's important to know that this is what you're solving. If I want to know where this function is increasing, I need to figure out where its derivative is outputting positive signs or positive tangent slope. And if I want to know where it's decreasing, of course we have to find it when our tangent slope is negative. Those are pretty trivial inequalities. Of course, feel free to do this question this way, but again, we're trying to set up a method that's a little more flexible and able to handle more difficult situations. And so I think the tool of choice here will be a number line. So if we draw a number line, and this number line is going to reflect the signs or show us the signs of our first derivative and where our first derivative is positive and where it's negative. So in order to set this up properly, we need to determine the critical values of our first derivative. So instead of worrying about where the derivative is negative or positive, We're going to figure out what makes that derivative exactly 0. That will be our critical value, and that's the one number in this case we'll put on our number line, and we'll use a number line sign test to solve this pretty straightforward inequality. So where's this derivative equal to 0? Of course, that's going to be 2x minus 4 equals 0. And we can add 4 to both sides and divide by 2, and figure out that at x equals 2, this is going to be the location of our critical value, and put it immediately on our number line of our number line test. So again, beware of critical values for a function or any x values that make your first derivative either equal to 0 or undefined. And we don't have to worry about anything strange with the quadratic or any polynomial for that matter. There's no way our first derivative can be undefined here. So we only have one critical value, so we chop up our number line in 2 pieces with that critical value right in the middle, and we simply do a test on the left, to the left of that critical value, and we input any number that's to the left of 2 into our first derivative. Of course, we can use a lot of different x values there, but I think I'll use 0. A little bit less thinking involved, and when we input 0 into our first derivative, we get 2 times 0 minus 4, which is negative. And on the right hand side of our critical value of 2, we'll test something in our first derivative, and the number 3 works as well as any. When we put 3 in our first derivative, we'll get 6 minus 4, which of course is going to be a positive 2. So our first derivative is positive to the right of 2, negative to the left of 2. And there's a couple of ways you can denote that on your number line, but you'll see in my answer key, I tend to prefer just putting a couple of pluses or a couple of minuses, staggering them on either side of your critical value. So negatives to correspond to all the negative tangent slopes that exist to the left of x equals 2, and some positives to correspond to the positive tangent slopes, of course, that exist infinitely to the right of 2. And as soon as you see that, hopefully you clue in that these are negative tangent slopes, so my function is decreasing to the left of 2, and it's increasing to the right of 2. And if you're thinking to yourself, wow, this is a lot just for a quadratic, well, it is, honestly, but we're trying to get ready for more difficult situations coming in future videos. Okay, so what's left here? I guess we don't have to talk about it because it hasn't been mentioned in this question, but we should probably sort out some of the terminology as well. So we have a critical value, right, and that's what made our first derivative equal to 0. And that critical value, because it made our first derivative equal to 0, establishes that we have a stationary point here. Right, so there's a stationary point at x equals 2, and I'll just put f of 2. And why is it stationary? Well, its tangent slope is 0, so it means the function's standing still. So stationary point, and if it's standing still, it can't be increasing or it can't be decreasing, which is why we're trying to stagger our pluses and minuses on our number line test on either side of that critical value. A stationary point can also potentially be a turning point, but remember what we need to see. We need to see a change in direction of our function. And again, there's no surprise with our quadratic. We know it changes direction, but if our function's going down, I'll just kind of make this an imaginary tangent line. If our function has negative tangent slopes, and then a 0 tangent slope, and then positive tangent slopes, you can probably see that seems to be tracing out the contour of a minimum value. But for now, let's not worry about that stuff. We'll deal with that in future videos. Let's just make sure we're clear that the function has changed direction because it's gone from decreasing to increase. So we're going to also note that, of course, this point 2 and f of 2 is also a turning point, because of the change in direction, because the function turns around. So maybe we shouldn't have dealt with that too much right now, because I think it's important to sort out some of all the new terminology that we saw in this video, because our focus really should be just listing off our intervals. So let's do that and wrap up. So where's our function? What's our function doing from left to right? Well, our function is decreasing, first of all. I mean, that number line diagram does a pretty good job of describing everything, but I'll just be a little bit more formal, at least in this video. We'll say f of x is decreasing. We'll actually list the interval because you're being asked for the interval. And we'll just say over the interval where x belongs. And instead of using an inequality, we'll use interval notation, which remember is round brackets for an open interval. It doesn't include these endpoints. Of course, we don't want to include negative infinity, and we definitely don't want to include that critical value there of x equals 2. So that's saying 2 to the left of 2 all the way towards negative infinity. This function is decreasing and going down. And then f of x after that is, of course, increasing. Over x, and that's supposed to be an epsilon. The first one was a little rough. So x belongs to this interval of 2, but not including 2 all the way to the right forever towards positive infinity, but of course not including positive infinity. And if you're a little rusty with your interval notation, I'm sure you'll get used to using it if you already haven't. Okay, so those are our intervals. We'll just box those. And keep in mind, I guess, as we wrap up here, stating the intervals is honestly a little bit of a nuisance. Quite often we're just trying to use those intervals of increase and decrease to pinpoint whether we have a turning point or not. But in this question, we're being asked to state those intervals or find those intervals. So that's why we have to make sure we write them out. And of course, make sure you understand that an interval notation is probably a little bit more efficient and more commonly used in calculus than writing inequalities as well. So there we have it. We've dealt with increasing and decreasing intervals for a very basic function. F of x equals x squared minus 4x, and in subsequent videos we'll up the ante. We'll look at some more difficult functions, and we'll continue to look for these intervals.